Black holes. You think you know them. A dead star, a pit in space, a place where nothing escapes. But that picture is just one kind of black hole, and it barely scratches the surface. There are at least 5 different types. Some are smaller than a city. Some are heavier than an entire galaxy. Some spin so fast they drag space itself around like water in a drain. And some might not have come from stars at all. They might be older than the first star that ever shined. Today we're going through every type of black hole, from the smallest the universe can make to the strangest things hiding at the center of galaxies. By the end, you'll never think of a black hole as just one thing again. Let's start at the bottom and work our way up. Stellar black holes. We begin with the classic, the one you already picture in your head. This is what happens when a massive star dies. To understand it, you have to understand what a star actually is. A star is not a peaceful ball of light. It's a constant, violent war. Gravity is always pulling everything inward, trying to crush the star into a point. Pushing back against it is nuclear fusion in the core, where hydrogen is being smashed into helium, releasing enormous energy that pushes outward. For millions or billions of years, these two forces are almost perfectly balanced. The star holds its shape. It's a standoff. But a standoff can't last forever. Eventually, the star runs out of fuel. The fusion in the core sputters and stops. And the instant it stops, the war is over. There's nothing left pushing outward. Gravity, which never tires and never stops, finally wins completely. The core collapses. And it doesn't collapse slowly. The inner core of the star falls inward in less than a single second, slamming together at a quarter of the speed of light. What happens next depends entirely on how heavy the star was. If the star was medium-sized like our sun, it leaves behind a white dwarf, a dense ember. If it was heavier, the collapse is stopped by neutrons, and you get a neutron star, a city-sized object so dense a teaspoon of it would weigh billions of tons. But if the star was truly massive, more than about 20 times the mass of our sun, nothing can stop the fall. Not electrons. Not neutrons. Nothing. The core crushes past every limit physics knows and keeps going, collapsing into a single point. A stellar black hole is born. These are the most common black holes in existence. They typically range from about 3 to 50 times the mass of the sun, all squeezed into a region only a few kilometers across. Our galaxy alone is thought to contain millions of them. And here's the unsettling part. Most of them are completely invisible. They drift through the galaxy silently, emitting no light, giving away nothing. We can only spot one when it happens to be feeding on a companion star, ripping gas off it. That gas heats up as it spirals in, glowing in X-rays we can detect from Earth. So every stellar black hole we've found is one that happens to be eating. The silent ones, the lonely drifters, we have almost no way to see at all. There could be one passing through our region of the galaxy right now, and we'd never know. Let's put their size in perspective, because the numbers are deceptive. A stellar black hole with 10 times the mass of the sun would have an event horizon only about 60 kilometers across. That's smaller than many cities. You could fit the mass of 10 suns into a sphere you could drive across in an hour. That is how absurdly dense these objects are. And they come in subtle varieties of their own. Some stellar black holes are born quietly, the stars simply winking out and collapsing without much fanfare. Others are born in one of the most violent events in the universe, a supernova, where the outer layers of the dying star are blasted across space in an explosion that can briefly outshine an entire galaxy of 100 billion stars. A small fraction may even form in hypernovae, linked to gamma-ray bursts, the most energetic explosions known since the Big Bang. So even within this one category, the smallest and most common type, there's a whole spectrum of births, from a silent fade to the most violent fireworks the cosmos can produce. But as strange as these are, they're the small ones. To find the real giants, we have to go to the center. Supermassive black holes. Now we scale up. And not by a little. By a factor of millions. At the center of almost every large galaxy in the universe, including our own, sits a monster. A supermassive black hole. These range from millions to billions of times the mass of the sun. The one at the heart of our own galaxy, the Milky Way, is called Sagittarius A star. It weighs about 4 million times the mass of the sun, and it sits 26,000 light-years from where you're standing. As enormous as that sounds, it's actually one of the quieter, smaller supermassive black holes. Others are almost beyond comprehension. Some reach tens of billions of solar masses. The largest known ones are so big that their event horizon would swallow our entire solar system many times over. In 2019, humanity took its first ever direct image of one of these giants, in the galaxy M87, and a few years later imaged Sagittarius A star itself. We finally saw the shadow of a monster. But here's the problem that keeps astronomers awake at night. We don't actually know how they got so big. A black hole grows by eating, by pulling in gas and stars and merging with other black holes. But eating is slow. There's a limit to how fast a black hole can consume matter, because the matter falling in glows so brightly it pushes the rest away. And here's the contradiction. When we look at the most distant galaxies, the ones we see as they were just a few 100 million years after the Big Bang, we already find fully grown supermassive black holes. Billions of solar masses, fully formed when the universe was still a baby. There simply hasn't been enough time for them to grow that big by feeding alone. So how did they form so fast? That is one of the single biggest unsolved questions in all of astrophysics. Maybe they started from enormous seeds. Maybe entire gas clouds collapsed directly into black holes without ever becoming stars. We genuinely don't know. To really feel how strange this is, consider the scale of one of these giants. The supermassive black hole in galaxy M87, the first one ever photographed, has a mass of about 6.5 billion suns. Its event horizon is so large that light, the fastest thing in existence, would take days to cross it. Around it spins a disk of superheated gas, and from its poles it fires jets of plasma thousands of light years out into space, beams so powerful they shape the evolution of the entire galaxy around them. These black holes are not passive pits. When they feed actively, they become the brightest objects in the universe, called quasars, outshining every star in their host galaxy combined, visible across billions of light years. The light from the most distant quasars has been traveling toward us for almost the entire age of the universe. So when astronomers say they see fully formed monsters in the early cosmos, this is what they mean. They are looking at blazing beacons that existed when the universe was a tiny fraction of its current age, and somehow those beacons were already powered by black holes billions of times heavier than the sun. But that contradiction points us toward a missing piece in the middle: intermediate black holes. If small black holes come from stars, and giant ones sit in galactic centers, there should be something in between. A middle class. Black holes weighing hundreds to hundreds of thousands of solar masses. Big, but not monstrous. The bridge between the two extremes. And for a very long time, this is exactly where the story broke down. Because we could barely find any. It was a glaring gap in the data. Think about it logically. If supermassive black holes grew from smaller ones merging together, the universe should be absolutely littered with intermediate ones at every stage along the way. They're the necessary stepping stones. But for decades, the middle of the range was nearly empty. It was as if we'd found babies and full-grown adults, but almost no teenagers. Something was wrong with either our theories or our search. In recent years, that's finally starting to change. We've begun catching them, often hiding in dense globular star clusters, ancient tight-packed balls of hundreds of thousands of stars where black holes can sink to the center, collide, and merge. Gravitational wave detectors have also caught the ripples from black holes merging into this intermediate range, giving us direct evidence they form. These middleweight black holes may be the seeds, the crucial link that grew into the supermassive giants anchoring galaxies. The missing link slowly being found one detection at a time. There's a deeper reason astronomers care so much about finding these middleweight black holes. They're a test of the entire growth story. If the universe really does build its giants by stacking smaller pieces together over billions of years, then the intermediate range is the assembly line, and it should never be empty. Finding them, measuring how many there are and where they live, tells us whether our picture of cosmic history is right or whether we're missing something fundamental. Each new detection in this range, whether from a star cluster that's behaving strangely or from a gravitational wave rippling out from a distant merger, is a data point in one of the most important construction projects in science, the effort to explain how the largest single objects in existence came to be. But the next type didn't come from stars at all. To find it, we have to go back to the very beginning of time. Primordial black holes. Every black hole we've talked about so far comes from matter collapsing, usually a dying star. But there's a proposed type that needs no star, no death, no collapse of anything that ever lived. These are primordial black holes, and they may have formed in the first fraction of a second after the Big Bang, before a single star existed anywhere in the cosmos. Picture the universe in its first instant. Unimaginably hot, unimaginably dense, energy-packed everywhere. But it wasn't perfectly smooth. Some regions were slightly denser than others. And in the most extreme of those dense pockets, the concentration of energy could have been so great that the region simply collapsed in on itself, folding directly into a black hole. No star required. Just raw, compressed energy from the birth of the universe pinching off into a knot in space. Here's what makes them so fascinating, and so different from every other type. They could be almost any size. Because they didn't form from a star with a minimum mass, a primordial black hole could be as light as an asteroid or as heavy as a mountain crushed into a space smaller than an atom. The size depends only on how big the dense pocket was. And here's the truly wild idea. Some scientists think primordial black holes could be the answer to one of the deepest mysteries in science. Dark matter. Roughly 85% of all the matter in the universe is invisible. We can't see it, we can only feel its gravity holding galaxies together. We have no idea what it's made of. What if it's made of countless primordial black holes, scattered everywhere, silently bending space with their gravity, but emitting no light at all? It's a stunning possibility. The catch is that we have never confirmed that a single primordial black hole actually exists. They remain theoretical. But if they're real, they might be hiding in plain sight, drifting through every galaxy, making up the invisible scaffolding of the entire universe. There's another reason primordial black holes are so tantalizing. They would be a window into the very first moments of the universe, a time we can otherwise never directly see. The conditions needed to form them depend on exactly how lumpy and uneven the infant universe was, so finding even one would tell us something profound about physics in the first instant of creation. Scientists are actively hunting for them in clever ways. They look for tiny flashes as the smallest ones evaporate. They watch for the way a passing primordial black hole would briefly bend and magnify the light of a distant star, a trick called gravitational microlensing. So far, these searches have mostly ruled out certain size ranges rather than finding anything, narrowing the hunt. But the search continues, because confirming a single one would rewrite multiple chapters of physics at once. And that idea of black holes shrinking and vanishing leads us straight to the strangest type of all, micro black holes. Now we go to the absolute smallest end of the scale. Micro black holes. Objects so tiny they defy intuition, possibly smaller than a single particle. And this is where the physics gets genuinely strange. For a long time, everyone assumed black holes only grow. They eat, they get bigger, they never give anything back. Black, after all, meant nothing escapes. Then, in 974, a young physicist named Stephen Hawking proved something that shocked the field. Black holes are not truly black. Due to the bizarre rules of quantum mechanics at the event horizon, black holes slowly leak energy. They radiate. And over unimaginable spans of time, they shrink, and eventually they evaporate completely. This radiation is now called Hawking radiation. And here's the key twist. The smaller a black hole is, the faster it evaporates. A giant supermassive black hole evaporates so slowly it would take vastly longer than the current age of the universe, almost forever. But a micro black hole would radiate furiously, blazing away its mass and vanishing in a brilliant flash almost the instant it formed. This is why micro black holes can't stick around. The universe makes them, if it makes them at all, only for the tiniest sliver of time. Some theories even suggested that our most powerful particle accelerator, the Large Hadron Collider, might briefly create micro black holes when it smashes particles together at near light speed. This caused a brief public panic that we might create something dangerous. But the physics is reassuring. Any micro black hole created would be so small it would evaporate instantly, harmlessly, before it could ever swallow anything. To this day, none has ever been detected. They sit right at the edge of what physics even allows to exist, the smallest possible objects the universe might be able to make. There's something poetic about Hawking's discovery hiding inside this. It connected three of the deepest areas of physics at once: gravity, quantum mechanics, and thermodynamics, the science of heat. It showed that black holes have a temperature and slowly cool the universe by evaporating, just like a hot coal radiating into a cold room. For the giant black holes, this process is so slow it's almost meaningless on any human or even cosmic timescale. But for the smallest ones, it's everything. Their entire existence is a brief, brilliant flash followed by a final burst of radiation as they vanish. In a strange way, the smallest black holes are the only ones we might ever watch die, while the largest will outlast almost everything else in the universe, fading away long after the last star has gone dark. But size isn't the only way to sort black holes. Two black holes of the exact same mass can still be completely different objects. How they spin. Here's a way of dividing black holes that has nothing to do with size. Rotation. The simplest possible black hole is one that doesn't spin at all. It's described completely by just a single number, its mass. That's it. It is, in a sense, the most perfectly simple object that can exist in the entire universe. But here's the thing. Almost no real black hole is like that. Real black holes spin, and they don't spin gently. Because they form from collapsing, rotating stars, or swirling gas, they inherit all that rotation and concentrate it. Many black holes spin at nearly the speed of light at their edge, turning thousands of times per second. And a spinning black hole does something a still one cannot. It drags space itself around with it. Imagine setting a spinning ball into thick honey. The honey near the ball gets pulled into the swirl. A spinning black hole does this to the fabric of spacetime, twisting it, winding it up around itself. This dragged region just outside the black hole is called the ergosphere. And remarkably, the physics says you could actually steal energy from a spinning black hole's rotation if you dropped something in just the right way. The spin changes how matter falls in, how the surrounding disk glows, and how powerful the jets blasting out of the poles become. So two black holes can have the identical mass and yet be utterly different objects. One a simple sphere, the other a roaring cosmic turbine winding up the fabric of reality. In fact, physicists have a famous way of summing up how few things define a black hole. They say a black hole has no hair. It sounds strange, but it means something precise. No matter what fell in to create it, whether it was made of stars, gas, antimatter, or encyclopedias, the finished black hole can be described by just three numbers: its mass, its spin, and its electric charge. Everything else about whatever fell in is erased, hidden behind the event horizon. So all that complexity, all that information about what the black hole used to be, is reduced to three simple properties. It's one of the most elegant and unsettling facts in all of physics, and it leads directly to some of the deepest puzzles scientists are still arguing about today. Which finally brings us to the question everyone really wants answered. What is actually inside one? What's inside? Every single type of black hole we've covered, from the micro to the supermassive, shares one defining feature: a boundary called the event horizon. It's not a surface, not a wall, not anything solid. It's a line in space marking the point of no return. Outside it, escape is possible. Cross it, and escape would require traveling faster than light, which nothing can do. So once anything crosses the event horizon, it is gone from the rest of the universe forever. Not because of a wall, but because every possible path forward now leads deeper in. And what waits at the very center? Our best equations give a disturbing answer. They point to a singularity, a point of zero size and infinite density, where space and time curve infinitely and the laws of physics as we know them completely break down. The equations stop producing sensible answers. They divide by zero. The honest, humbling truth is that we do not know what is really at the center of a black hole. Our current theories fail there. It may require a complete theory of quantum gravity, which we don't yet have, to ever understand it. And the cruelest part is that the event horizon hides the answer perfectly. Whatever happens inside can never send a signal out. It may be the single place in the entire universe that we are forbidden from ever observing, no matter how clever or determined we become. The black hole keeps its deepest secret sealed behind a one-way door. The takeaway. So let's pull it all together. A black hole is not one thing. It's a whole family of objects, related by gravity but wildly different in nature. There are stellar black holes, born from the death of massive stars, drifting in the millions through every galaxy. There are supermassive black holes, monsters anchoring the centers of galaxies, that grew impossibly large, impossibly fast in ways we still can't fully explain. There are intermediate black holes, the long missing middle children, finally being found in dense star clusters. There are primordial black holes, possibly older than the first star, possibly making up the invisible dark matter that outweighs everything we can see. And there are micro black holes, blazing at the very edge of physics, evaporating almost the instant they form. Sort them by size, and they span from smaller than an atom to larger than a solar system. Sort them by spin, and the same mass can be two completely different beasts. Sort them by origin, and some come from dying stars, while others come from the birth of the universe itself. But every one of them does the same three things. It bends space, it traps light, and it guards a secret at its center that we may never be allowed to reach. The universe, it turns out, is full of doors that only open one way, and we are only just beginning to learn how to count them. Not bad for stick figures on a rock.